Minerals are not inert, and in fact, they are continuously interacting with the fluids around them, most importantly with water. The case of clays is of particular interest for two reasons. One is charge, which will become apparent in the next few minutes. The other one is that because clay particles are small, they have very high specific surface. Therefore, the impact of having 10 monolayers, 30 angstroms of water affected on the surface is very important. However, 30 angstroms on a big clay sand particle is totally irrelevant. So it's not that that adsorbed layer is not there, it will be there, but it is much more important on the behavior of clays. Therefore, we're going to focus our attention on clay-mineral interaction, but there may be reasons why you may want to extend this to other geomaterials. So if you review the clay mineralogy, there is one comment that I purposely left for this presentation, and that is that sometimes during the formation of the silica tetrahedron, there may not be enough silicon, but the sheet is already formed. And so there is some aluminum left, and they bring the aluminum into the structure. So now you have a tetrahedron, but instead of having a silicon, it has an aluminum, and that means that instead of balancing four positive charges, now it has only 3 positive charges to contribute. Therefore, the system is not totally electrically neutral. Similarly, the aluminum octahedron, all the sheet is forming, but some aluminum is missing, but the structure is there, and there is magnesium in the medium during the clay precipitation, and so they grab a magnesium, they put it inside the octahedron. It doesn't totally neutralize the charges of the hydroxyls, but it's better than nothing. Once again, there is some excess negative charge. This idea of replacing a higher valence cation for a lower valence cation is while preserving the structure is called isomorphic, same structure, substitution. So clay minerals will have charge, and one of the reasons for charge is isomorphic substitution. Once again, silicon 4 positive may be replaced by aluminum 3 positive in the tetrahedral sheets, or aluminum 3 positive may be replaced by magnesium 2 positive in the octahedral sheet, leaving behind uncompensated negative charges. There is one more reason why clays may gain charge. This is going to be quite permanent, but they may also gain charge as they interact with the pore fluid. Let's remember, for example, a 2-to-1 clay, a 1-to-1 clay, kaolin. This is the octahedral sheet, so on the boundaries here, we're going to see hydroxyls. This is the tetrahedral sheet, so on the boundaries we see oxygens. If the pore fluid has low pH, that means that we added to water. Remember that pH 7 means that there is 10 to the minus 7 moles of self-ionized water molecules per liter of water. If we add more hydrogens, like for example hydrochloric acid, so we increase the concentration of hydrogen, then the pH will decrease. while if we increase the concentration of hydroxyls, then the pH will increase, an acid and an alkaline environment. Well, look what you have on the edge. It's either oxygens or hydroxyls, and they like that composition of water. So these ions are going to become charge-defining ions for the clay surface. In particular, when you have too many hydrogens, the hydrogens will come and they will protonate the surface, and now the surface, the surface charge, of the clay will become more positive. However, in the opposite case, it will deprotonate these hydrogens, and the surface charge becomes more negative. In fact, I could run an experiment in which I do what is called electrophoresis, which we explore in some other presentation. I gradually change the pH in an electric field, and I see whether the particles migrate to the left or to the right, so I can see what is the charge of the particles. And we will see that at some point, the particles were migrating in one direction and then in the other direction, and at some point they don't migrate at all. And at this pH, where the particles do not migrate, they say this is the electrophoretic mobility. When that mobility is 0, that is when the particles have no charge. So this is the point of 0 charge for the particle. Actually, we can explore this further and look at what happens on the surface and on the edges. And at low pH, it becomes positively charged, while at high pH, it becomes negatively charged. So now we have two reasons for charges on the clay. One is a stable charge, which is due to isomorphic substitution at the time of clay precipitation. And the other one is due to the interaction between the clay and the pore-fluid. And in more acidic environments, the charge becomes increasingly more positive. Now that we've recognized that clays may be charged, let's look at a dry clay. Because the Coulomb force, QQ over R squared, is so strong, nature tends to be electrically neutral. Under very rare conditions, we may find locally and probably on a transient that there is net charge. So if nature wants electron neutrality and the clay has an internal negative charge, then there must be counter charges to neutralize that one. And indeed there are. And there will be cations adsorbed onto the surface, and the most typical one will be sodium, potassium, calcium, and magnesium. And they will be there as many as needed to neutralize the clay. Furthermore, in soils we always have waters that have permeated with dissolved salts. If we dry the soil, those salts will precipitate. For example, we may have a sodium chloride crystal that has precipitated. This is a dry soil. Charged clay particles neutralized by counterions, cations in this case, and precipitated salts. Now, what happens when we add water and we wet the clay? Well, water molecules, remember these dipoles that are going to be vibrating and knocking and punching, they're going to do the following. First of all, they will encounter the salt, and they will hydrate the salt, where this will be the sodium, somewhere here will be the chlorine, and the chlorine being negative, it will attract the water molecules like that. And the sodium being positive, it will attract the water molecules like this. And so this is going to determine, those precipitated salts are going to determine the electrical conductivity, the ionic strength of the pore fluid. On the other hand, when water molecules reach these sodium, potassium, calcium, magnesium ions, they are also going to begin knocking at them. So let's say that we have a positive ion, a cation here, and water molecule comes in, and so the water molecule will put the tail like that, and then the ear will rotate and will go towards the clay, and because they are bouncing and they are going to kick out the cation, and so this cation will be rejected and it will hydrate, so that now we are going to have another cation which was originally on the surface of the clay, which is going to be removed from the clay surface because it becomes hydrated. Some cations may remain, and there will be other water molecules vibrating, pivoting around the negative charges. Clearly, folks, this unit that you see here is a still charge. The water is electrically neutral, but the cation is positive, so this whole unit of the hydrated cation is attracted to the clay, and the only reason that is pushed out is because of thermal vibration of the water molecules. Similarly, the original sodium from the hydrated salt will be attracted, and the anion will be repelled. It cannot go too far because this one is also attracted to the hydrated cation, and so they want to move further away because of thermal agitation leading to diffusion, but at the same time there is this whole balance of electrical interactions taking place between them. This is a wet clay. Let's summarize. Precipitated salts hydrate and determine the ionic strength, the electrical conductivity of the pore fluid. The originally counter ions that neutralize the clay charge get hydrated and for the most part get kicked out, but they cannot go too far because they are electrostatically attracted, and water molecules are adsorbed near the surface, hydrating the clay surface. Let's see if we can understand this region and do some statistics about the counter-ion cloud. Let's draw again the clay surface with its negative charges, the hydrated counter-ions that were originally here, but now they got hydrated by the water molecules, and they are kicked out of the surface. Some water molecules adsorb onto the surface, wetting the surface, and the precipitated salts, we had the sodium chloride hydrated also in the vicinity of the clay surface. And of course, some free water molecules in the system. If I draw and I take slices and I measure how many charges I have, and I plot the charge concentration versus distance, this is what we are going to find out. That there is high charge concentration near the surface because the counter-ion charges are attracted, but the counter-ions decrease with distance, and at the same time the anions don't want to be close to the negative surface, so there will be none of them, but as we move further away, they are diffusing in and out of this space. And so this is the distribution of negative charges away from the clay surface, where this is the distance x to the clay surface. So these are the distribution of concentration versus distance x for cations and anions. If I integrate the difference in charge, what is not neutralized, and by the way, I'm assuming that both of them are of equal valence, otherwise I have to compensate for the valence. If I integrate, this must be the surface charge. So the integral from 0 to infinite of the volumetric excess charge at distance x times dx is going to be equal to the surface charge of the clay. The number of charges I have per meter square, coulombs per meter square. What else can I tell? This concentration here, the asymptotic value of the concentration, this one is determined by the excess salts. That precipitate when you dry. So if I wash the soil and I get rid of all the excess salts and I wash it with deionized water, then the anions go to 0 and the cations will decrease towards 0 on the axis, and I will only have excess cationic charges. Now a new concept comes about, and that is work. The work that I have to do to push a test charge against the surface. And work in electrical context is like potential energy, is voltage. And so as I have a test charge, and let's say that I'm going to take a negative test charge, 1 electron, and I grab the electron and I begin walking, I'm going through an electrically neutral far field condition, nothing happens, but then as I begin experiencing this excess charge, I have to begin pushing more and more and harder until I get to the surface and I have done the maximum work. It's like lifting a body and adding potential energy. So if I plot the work that I have to do versus x, this is going to be, and we're going to call this the potential, this is going to be an exponentially decaying function like that, where this is V0, the surface potential, and the rate of decay is an exponential, so I don't have a characteristic length scale. But if I divide V0 by 1 over E, then this is a characteristic length which we're going to call beta. And that characteristic length gives me an idea of how thick this counter-ion cloud is. Sometimes this is called the thickness of the double layer, or physicists would call it the Debye-Huckel length. The reason why this equation is of the following nature, V0 e to the minus x over beta, is because this trend in this charge distribution, the second derivative of the potential in x is equal to the local charge density over the permittivity of free space and the dielectric constant of the pore fluid. And so a solution to this equation, this is called the Poisson's equation, and that comes from Gauss's law. The solution for that equation is this exponential, and that predicts the thickness of the double layer. If you follow this analysis carefully, and this is in our book, but probably a classical reference in the geotechnical literature would be the book by Jim Mitchell, now Soga and O'Sullivan as co-authors. The thickness of the double layer is proportional to the square root of temperature, permittivity, that permittivity that is here in the denominator, divided the valence square and the concentration in the pore fluid. This ionic concentration and the valence of these ions are determining how fast these get squeezed. What this is telling us is that if the valence and the concentration increase, the thickness of the double layer decreases. In other words, I shield the charges at a shorter distance. When valence and concentration increase, this line, this exponential, drops much faster, and I'm shielding the surface charges in a shorter distance. There are a few more details to this derivation, which, by the way, dates from the 1910s. And that is Gouy and Chapman theory following earlier work by Helmholtz. But they made an important assumption, and that was that charges were point size. Let's correct for that, and we are going to come up with few other definitions that will be relevant to the discussion. The Poisson equation and Gouy-Chapman's derivation presumes that charges are point size. However, charges, particularly as we approach the surface, charges, of course, they have size, but that becomes particularly important when we approach the surface. In fact, sometimes the charges cannot be truly hydrated out, and so they remain attached to the surface, and so this will be the water molecules here. And these are called inner sphere complexes. Sometimes a water molecule will get attracted here, and there is a direct association thereafter of the counterion charges to the water molecules, and these are outer sphere complexes. But they have really quite a close proximity to the clay surface, and they are not so mobile. For example, they will not contribute fully to the electrical conductivity, in other words, to the mobility of ions when I apply an electric field. Of course, these counterion charges, both positive and the negative ones, will be very mobile and will be the cause of electrical conductivity, but not these ones. And so when I come back to push the electrical charge and I push, I see this exponential increase in the potential, but then when I approach that layer, I cannot think that that is an exponential decay anymore. And in fact, who knows how I go from here to here? There is a quantum jump in this atomic scale, which is going to be 2-3 angstroms in thickness. These are just a few angstroms in thickness. And so up to this point, I can track it with an exponential decay, but not thereafter. This is the surface charge. The limit of the exponential increase, it has a name, is the potential at the stern layer. And it's basically measured few angstroms away. Now, if you remember that I mentioned earlier that I could put a clay particle in water and I apply an electric field and see if it moves to the left or to the right. Well, this is the clay particle with a counterion cloud, and when I pull it, electrically pull it, not all the counterion cloud remains behind. In fact, I am shearing this at some distance from the clay particle. So when I do the computation of what is the surface charge that I measure based on the mobility of particles, I'm not really looking at the surface of the particle. I'm looking at the distance away from the surface along this shear plane. And so if the shear plane is somewhere here, then this is going to be called the zeta potential, where this is the shear plane. Finally, at some distance away, when we divide the surface potential by 1/E, I determine the thickness of the double layer in this. Now the question is, which is the potential that I'm dividing by E? Because if the surface potential is not accessible, then I am actually dividing by the stern potential. And so read the literature very carefully to see which is the actual potential that is being taken into consideration when you determine all these quantities and the methodology and the hypothesis in the interpretation of those charges. Let's conclude this presentation with some heuristics. You may still remember that we talked about the thickness of the double layer being affected by temperature, which is thermal activity. It kicks things further away. The dielectric constant, which is the polarizability of the medium, let's say for water, 80. The valence of the prevailing ions and the concentration of the ions. You can see valence is very important because one charge or two or three valence can counteract respective number of charges on the surface. But while valence is very important, concentration plays a critical role because concentration can vary in orders of magnitude from fresh water to salt water to brines. And so keep an eye on concentration above all. And remember that when either concentration or valence are high, the thickness of the double layer is shorter because the counter-ion charges are cancelled out with a narrower diffuse double layer, a narrower counter-ion cloud. So now we can come up with the following heuristics. Given two particles at a certain distance between them, which we're going to call delta, if I plot the double layer from the left, it would be like that. The double layer from the right would be like that. And that interaction means repulsion. On the other hand, if the surface charges are cancelled at the very short distance because the thickness of the double layer is short, then there is virtually going to be no repulsion. So we can recognize that repulsion between particles, pushing them away, is going to increase when the thickness of the double layer increases. With that in mind, now let's consider several examples. Remember what determines the thickness of the double layer. So example number one, imagine that we put a pile of salt on the ground, and eventually this salt begins dissolving and invading the subsurface and diffusing, and an ionic concentration front either moves closer to some construction, so the concentration increases either by diffusion or advection. If the concentration increases, the thickness of the double layer decreases, therefore repulsion decreases, and this we'll call contraction. And that could be the form of settlement, for example. So if you have a house here, it would experience a differential settlement because of this invading front. Let's consider another example. We are going to build a dam to hold seawater. And so this is the sea, and this is probably quite important for sea level rise as we begin to develop coastal protection systems. We compacted the dam with fresh water, and then when the sea level goes up and it begins permeating, and you can draw your flow net, the concentration is going to go up because you compacted with fresh water. If the concentration goes up, two things may happen: settlement, but along the length of the structure, there will be contraction, and there may be transverse cracking. Now, to prevent that, you may decide to then compact the dam that you're going to use to control the sea level rise. You may decide to compact it with seawater. Now, what happens next is also tricky because it begins raining, and as it rains, the concentration actually will go down. And because the concentration goes down, the double layers are going to swell, and repulsion is going to increase and trying to repel neighboring particles, and therefore these systems are going to cause lots of surface erosion. And back clays along the Mississippi and similar structures probably result from this type of changes in ionic concentration in the compacted layers. We could think of other cases. Imagine that you compact a pond to retain organic material from an industrial site or from oil, could be from some solid waste that eventually leaks off oil, and now oil tries to invade the system, which was compacted with fresh water. This is the clay liner, and so this is going to be more complex because we have a mixed fluid condition, we have capillary effects, etc. But if it was, for example, alcohol, which is truly fully soluble in water, and it will lower the permittivity. As the permittivity decreases, the double layer thickness will decrease. If the double layer thickness will decreases, there is less repulsion. In fact, contraction takes place, and so this is also going to cause contraction. While these are a little bit esoteric examples, in fact, they are based on real case histories that we have observed from Maracaibo Lake to the Orinoco to here in North America. The important message is that because the counter-ion clouds around clays are quite significant compared to the clay thickness, in other words, we are talking about high specific surface materials, then these coupled chemomechanical effects may gain relevance and may determine the long-term performance of our engineering structures. The second part of this presentation will be based on slides to show you a few more details and clearer sketches.